Okay, so we're talking about arc length today, and I'm going to derive the formula for arc length so it makes some more sense. So you can it'll help you memorize the formula. We'll do a problem from the extra credit assignment from the book. Right? Then I want to talk about surface area. Maybe we'll do a problem from the book there too. Depends on you guys. So arc length. Here's the idea: is you take some curve from A to B. And we want to find out how long that curve is, right? The length of the arc. Well, if there's a piece of string, that's easy. You take each piece, you pull it straight, you take out a ruler, and you measure it. Right? Unfortunately, for a lot of curves, you can't do that. Like the terrain of Earth, you can't just flatten Earth out and measure it. It doesn't work that way. So we need other tools to measure lengths of these curves. And the idea is if we zoom in on one particular, or if you zoom in far enough, you realize that it becomes basically a straight line, right? It becomes basically a straight line. It's a really small straight line, which we're going to call ds. Right? D for differential. And that has an x component and a y component, so you can sort of think of it like a vector, if you want. And the x component is your dx, and your y component is your dy. And this is the right triangle. So, fundamentally at the heart of the arc length formula is the Pythagorean theorem. So we talked about finding volumes of solids. And when we talked about finding volumes, we said you take the integral, and what the integral does is it slides area, and sliding area creates volume. So for this, sliding a point creates a line. And because of our concept of a limit, you can think of ds as basically a point, right? You're taking the limit as that goes to 0. So that's basically what we're doing. We're at the integral will add up all these small, point-like segments, and that will create the arc length. Right? That's how we construct the arc length. So the length is the integral from a to b of all these ds's. All right, that's what we're adding up, each ds. But then, here's the big idea, is I can now integrate, I can rewrite ds by using the Pythagorean theorem as the square root of dx squared plus dy squared. Because the Pythagorean theorem up here says that dx squared plus dy squared equals ds squared. Alright? Does that make sense, just in terms of where this comes from? Alright, now this integral that we have doesn't really make any sense. This integral is basically meaningless because we don't even know if we're integrating with respect to x, with respect to y. There's no dx or dy out here. All the dx's and dy's are cramped inside the square root symbol. So what's that all about? That's the question, right? What's going on there? So in order to turn this into something with meaning, we need to do some algebra tricks, which I'm going to walk through with you. And the first one is we're going to multiply this by 1. But we're going to be clever by how we write 1. We're going to write 1 times dx over dx. Because dx divided by dx is 1. So we're multiplying by 1. So now we have the integral from a to b times the square root. And I'm going to do another trick as well. Inside the square root, I'm going to factor out a dx squared. So dx squared divided by dx squared is 1. And then we've got dy squared over dx squared times dx squared dx over dx. So if I take this dx squared and distribute it through, we're back up to what I had in the blue. Right? So when you factor a number out of, when you factor dx squared out of dy squared, it just becomes dy squared divided by dx squared. Just write it that way. Alright, this is good because what's the square root of dx squared? Dx. So this piece cancels with the dx outside the square root.
Why did you choose dx just arbitrarily?
Yeah, because of what's about to happen right now. So we've got the integral from a to b. Inside the square root we have 1 plus dy squared over dx squared is the same as dy over dx quantities squared dx. So the thing is, I multiplied by dx over dx because the denominator will now cancel with this dx. And we're left with the dx in the numerator. Now all this stuff I'm doing is, it's very messy. Like, for math professors, you would have